Hello again. Welcome back to some more lectures about physics. This is chapter 16 from volume 2. As I told you guys a while ago, we'll be jumping back to electromagnetic waves after we did optics. Talk a bit about electromagnetic waves before we move on to the other stuff more described as modern physics. Right, so we talked a lot about light, sort of ray or particle-like aspect. Then with interference and diffraction, its wave-like properties. Yeah, we're really going to kind of codify what we mean by the wave nature of light, or how mathematically we describe the wave nature of electromagnetic waves. Light, well, visible light's one part of the electromagnetic spectrum. Here, just like all waves, electromagnetic waves carry energy, they can exert pressure, and the picture showing here is actually a comet that's going across the sky, but the tail of the comet very light and sort of light enough that the pressure from sunlight is actually able to push them a little bit, and so you actually see this sort of spread of that tail being pushed a little bit by the pressure from the sunlight. And we'll get to that later. Okay, so you can't really talk about electromagnetic waves without talking about this guy, Maxwell, who I happen to share a birthday with, funnily enough. He's sort of the giant in what we call classical electromagnetism, because he sort of synthesized, in a way, a lot of the information that was already out there about electricity and about magnetism, and a lot from these other physicists, Gauss, Faraday, Ampere, and sort of saw that they all fit together in a certain way, and added, corrected just a little bit, partly one to show that they really did fit together and you actually get the electromagnetic waves. So since it's been a little bit, probably since you thought about electricity and magnetism, for the second part of this three-part course, we're going to just do a quick recap of the very broad, big picture things in electricity and magnetism. And really it comes down to 4 equations, 4 plus 1. But one of those is known as Gauss's law, and it basically allows you to tell what the electromagnetic field is like through a surface, a Gaussian surface that you just draw out, imagine, as long as you know about the charge that's inside, electric charge that might be inside of that surface. Okay? So you probably went through plenty of times when applying this or thinking about how that works. Okay? But that's Gauss's law. You might not have seen this one yet. This is what's known as Gauss's law for magnetic fields. And it's very similar, it's essentially the exact same idea to figure out what a magnetic field is like, but assuming that there's like a magnetic charge inside of that Gaussian surface that you were to draw. As it turns out, there are no magnetic charges. That would be what we call the magnetic monopole. Right? We always find magnetic sources as plus and like the north and south pole together. There's no singular magnetic source. So what that means in terms of Gauss's law is that if you write it down, the right side of the equation is just 0. There's no sources, there's no magnetic charges in the way. Right? And then there was also Faraday's law, which basically said that if you have a magnetic field that changes in some way over time, that's going to induce an electric field. Right? It's going to produce an electric field. And the classic example of that is just have a loop of wire and move a bar magnet through that loop of wire, increasing and decreasing the magnetic flux through that wire, so you end up inducing a current. Or you produce an electric field, which pushes the charges in the wire. That's how you get your current. But basically, if you have a changing magnetic field, that will produce an electric field. That's kind of the Faraday's law in a nutshell. And then finally, we had Ampere's law, which allowed us to calculate the magnetic field if there was a current. So moving charges, electrical charges, will produce magnetic fields. Current is just another word for a flow of electric charges. Currents will produce magnetic fields. Thinking about the current through this surface, if you were to draw this loop in the picture, the loop is shown as the surface area A with the radius R, so circle. You draw this loop and think about the current running through this loop, then the magnetic field on the edge, that path is defined as by that ds. That path, you can figure out the magnetic field along that path. So pick that loop, whatever current's flowing through a surface bounded by that loop, or by that path, that's where you're thinking about your magnetic field, where you calculate a magnetic field. It turns out that Ampere's law has a little bit of a problem though. And Maxwell saw this, and Maxwell figured out how to kind of fix it, how to correct it. The thing with all these laws is when you're picking either a loop, in some of them, like Ampere's law, you pick a loop and the surface defined by that. Any surface bounded by that loop you can use for Ampere's law. In Gauss's law, both of Gauss's laws, you pick an actual surface, and anything through that surface tells you about what's happening on that surface. The thing is though, like with Ampere's law, if you pick that loop, like I said, any surface bounded by that loop, well, it should give you the same answer or the same result for the magnetic field around that loop. So in this picture here, if we think about, again, a current flowing through a wire here, I guess flowing downward, you pick this loop, the dotted yellow line there, and in the one surface that you could imagine bounded by that loop, there's a current flowing through it, so we would get a magnetic field that's produced around that loop. But again, I can just imagine a different surface that's still bounded by that loop, so you imagine sort of pressing that surface down. It's still all bounded by the loop here, right? But now the surface goes through this sort of area where there's a plate on one side and a plate on another side, right? But there's no actual current that's flowing in between these plates. So in surface 1, there's a current that pierces, that goes through that surface, so to get a magnetic field. Surface 2, there's no current that goes through that field, or through that surface, S2, so we shouldn't get a magnetic field. But they're both bounded by the same loop. So we should get the same answer because we're talking about that same loop, C, there. So this is the problem. And Maxwell's contribution was to come up with this sort of thing that we would call a displacement current. So it's something that acts like a current, so it can produce magnetic fields, but it's not directly from charges flowing. It turns out, displacement current, that thing that acts like a current, is a changing electric field, or technically a changing electric flux. So this is very similar to one of the other laws where you were looking at a changing magnetic field, magnetic flux, but this one has to do with the changing electric flux. And so if you have an electric field that changes, it acts as a current and produces a magnetic field. So, put all those together, we have these 4 equations, Maxwell's equations, we would call them now. And like I said, there's kind of +1 if you then want to think about the force on, say, a charge due to these fields that you get from Maxwell's equations. We need Lorentz's equation that tells us about the force, electric magnetic force on charges. But if you're just talking about those fields, there you go. Maxwell's equations tells you everything you need to know pretty much about electric and magnetic fields. By introducing this displacement current, which is the changing electric flux piece, this last term in Ampere's, the Ampere-Maxwell law now, Maxwell introduced a bit of like a symmetry in these equations. Right? So now this magnetic field relationship also has this term that's almost identical or analogous to the one in Faraday's law. Right? So now we sort of have this sort of symmetry going on, where these two are already kind of symmetric. This one was about charge. This one would have been about current or magnetic charge, but there is no magnetic charge. But they're still very analogous. So once he did this, I don't know the exact order and history of this, but once you introduce this new term, this displacement current term, this changing electric flux thing, well, now you have a changing electric fields will create changing magnetic fields create changing electric fields, and you get this sort of endlessly reproducing cycle, which sort of implies that you're going to have waves, you're going to have electromagnetic waves. And it's hard for us to imagine, what's going on at the time or like how people were thinking, but we know, for sure, before Maxwell brought this about and before the consequences of putting all these things together started to become clearer, it wasn't actually known at the time that light, visible light that we see, is even connected to the phenomenons of electricity and magnetism. So they had things, they were doing stuff with electricity and with magnetism, and they knew that they were connected, but there was also stuff about optics, and that was just like visible light. It was thought to be pretty different. But as I noted at the very beginning in chapter 1, the speed of light around that time was actually measured, and it had been measured earlier. It was measured fairly accurately, though, around that time. It was I forget what the actual measurement was, but they knew it was around 3 times 10 to the 8th meters per second. Most of this stuff that we interact with day in and day out is due to electrical magnetic effects. And the fact that just these 4 equations can basically describe the entirety of electromagnetism is mind-boggling to me. It's very kind of, beautiful in a way too. Yeah, so that kind of encompasses what you would call classical electromagnetism. There's also relativistic electromagnetism, and then we get into sort of the particle physics look at all of this stuff too, but we'll get to that later on probably, I think, or at least a little bit. And just to note too, there's multiple ways to write down Maxwell's equations. This one is what you would call the integral form, because it's in terms of integrals. There's also differential forms, you can write them in terms of differentials. It's also in standard units, SI units. You can also write them in terms of Gaussian units, where all of these constants sort of disappear in a way, just a different definition of some units. There's also one other way where this is, the way that these are written now, you're essentially talking about the fields themselves. You're like, these are microscopic sort of picture of electromagnetism. But if you're talking about electromagnetic fields in materials and sort of on a macro scale, it turns out it's a little bit better to work with some slightly augmented fields. So sometimes you'll see these in like the macroscopic version where the E and B are sometimes replaced by sort of scaled versions of those fields. Still the same fundamental equations. All right, think about the formation of these waves. If we imagine starting out with a wire that can carry a current, and we imagine that there's an AC current in this wire, right? Meaning that the charges essentially are going up 1 second and down the other second. Like they're constantly changing directions. So there's this movement of electrical charge just kind of up and down, up and down. So at one instant, maybe the charges are moving up, and if we think of Ampere's law, then draw a loop around that wire, and the current flowing through that surface that's bounded by that loop tells us that there's going to be this magnetic field around the wire. But now we could imagine, say, another loop, which from Faraday's law, if we draw that loop where that magnetic field is actually changing, right? The charges are constantly like speeding up and then slowing down, speeding up, slowing down, speeding up, right? So that's constantly changing. So the magnetic field that it produces is constantly changing, meaning that this loop, if I imagine drawing a loop where E0 is shown now, there's a magnetic field through that loop and it's constantly changing. So that changing magnetic field from Faraday's law tells us there will be an electric field produced by that changing magnetic field. So now at E0 we have this changing electric field looping around. And then again, if we go back to Ampere's law, now the Maxwell part of Ampere-Maxwell law, draw a loop through E0, that loop E0, draw this B1 loop, and there's E0 is a changing electric field that's going through that B1. So changing electric field produces a magnetic field that's also going to be changing. And you just get this continuous sort of avalanche of this process, the thought process, where this changing magnetic field produces the changing electric field, produces the changing magnetic field, produces the changing electric field, so on, so on, so on. And this is how we get to visualizing or thinking about the creation of electromagnetic wave. We constantly have this up and down with the electric field, side to side with the magnetic field. And given the fact that Faraday's law and the Ampere-Maxwell law have to do with the flux of the electric field and the magnetic field, the result of that is that these fields produced, like the electric field from a changing magnetic field, is perpendicular to it. And the magnetic field from that changing electric field is perpendicular to that electric field. Right? So in this process, all of these fields that we're imagining, the magnetic fields are all perpendicular to the electric fields. So if you want to know a little bit more about what that wave will look like now, kind of have to think back of what the actual source was doing, what the original current was doing. And it's going to depend on what that was doing. So if that AC current is like a sinusoidal one, right? It's going up and down and up and down and up and down in this sine sort of pattern, then all these fields that are produced are going to be sinusoidal as well. Just going to quickly jump ahead. We'll get into more detail why this picture looks like it does, but this is the end sort of result that we get is this electric field that's sort of sinusoidal and a perpendicular magnetic field that's also sinusoidal. We're going to work through a good bit of stuff until we get to that, but I wanted to just show you the picture real quick. Jump back. As I said earlier, Maxwell's introduction of this displacement current term, this changing electric flux term, introduced a kind of symmetry to all these equations. And we can really bring that out when we think about what the solution to these equations are in what we call free space, when there's no charges, there's no currents. So if you look at what happens to the equations in free space, well, Gauss's law for electric fields, this right side just becomes zero. Magnetic fields, it's always zero. That one's still the same. Faraday's law is the same. And then Ampere Maxwell, we lose the current, the first term on the right, because that's a current, and we're saying there's no currents, there's no charges in this space, in this area we're thinking of. Now we see really this kind of symmetric property of all these equations. They'll look very similar. These two are almost pretty much exactly the same. These two are almost exactly the same. Okay, so we're going to go through a fairly in-depth look at how we get to the solution to Maxwell's equations in free space. But we need to talk about some of the setup for this. I already said about what we mean by free space. Also, we're thinking about electromagnetic wave that's propagating in just in a certain direction, and we can define our coordinate system however we want. So we're going to define it so that the x-axis is pointing along the direction that the wave is propagating. Since we do that, the wave is parallel to the x-axis, and in a sense, its y and z position are fixed. There's no movement overall of the wave into the y direction or into the z direction. So what that ends up meaning is that the fields won't depend on y or z. They're just going to depend on x and time, so x and t. Right, and then the last thing to point out maybe about this setup is that we're going to imagine some Gaussian surfaces, some loops for Faraday's law or Gauss's law or Ampere Maxwell law. So this is the overall surface we're going to think of. It's this rectangular surface, and it has the vertical and horizontal, or say the z and the y dimensions are both L. The x dimension we're going to say is dx, or a delta x. Right? And when we talk about something as a delta, eventually we're going to think about that thing going to zero. Okay, so the first thing we're going to think of is applying Gauss's law. Just think about, say, the electric field, or Gauss's law for the electric field. Well, Gauss's law is talking about the whole surface, but let's just think about it piece by piece here. So say on the bottom side and the top side, right, side 1 and side 2, the only change from that bottom to the top is y, right? So this is a difference in y from the bottom to the top. But we already said that the fields don't depend on y, right? So that means that the field down at the bottom here is going to be the same as the field down at the top. And in terms of Gauss's law, that's telling us that overall, there's no net flux through this surface, out of the surface. The same amount of, say, you could imagine it as the same amount of flux is coming up through the bottom as is going out through the top. So overall, there's no net flux, top and bottom. Same idea, front and the back here, side 3 and 4. In the z direction, again, these fields are not depending on z, so there's no net flux through the front and the back. So the only flux we might get here is from the left side and the right side, right? And in the picture, the left side, it's not maybe exactly clear, but the picture has these coordinate axes on here, and one is showing on the left, is showing the electric field in x, y, and z directions when x is equal, just at x, right? X and at time t. And then a little bit to the left, there's another coordinate axis shown where we're thinking about the x, y, and z components of the electric field, but now we're at the position x plus delta x, right? We're on the other side of this little Gaussian surface, but still at time t, time's not changing. Okay, so what then does Gauss's law look like for the left side and the right side, right? At x and then x plus delta x. Well, technically this is Gauss's law for the whole thing because we already said that all the other sides cancel each other out. So on the left side, flux looks like this, and I'm just going to write A. A is just L times L. That's the area of the left side, also the area of the right side. But on the right side, we're at x plus delta x, still times a. Same surface area. And there's a difference in sign here, right? Because the surface on the left side is pointing in one direction. If you think about a normal vector to that surface pointing in the negative x direction, say, versus the a normal vector on this right-hand side is going to be pointing in the positive x direction. So this one, there's got to be a difference in sign. This is we'll call this one the negative sign. So Gauss's law would tell us that this should be equal to the charge enclosed divided by this permittivity, electric permittivity of free space. But we already said there's no charges. We're talking about free space. So Q enclosed is 0. Which I can just do this. So that actually means that these two things are equal to each other. And that's telling me that the electric field is not actually changing from the backside of this Gaussian surface to the front side. So another way of saying that is just that the electric field in the x direction is constant, right? Or it's 0. And if it's 0, fine, it's 0, we won't worry about it. If it's constant, that's fine too, but a constant electric field is not a wave. We're interested in the wave-like aspects. So if it is a constant value, that basically just means that we might have a wave that's overall in an area where there is also an electric field, like in one direction. But waves are these things that fluctuate. So essentially we're just going to say there's no electric field in the x direction. And we could go through basically the same argument for Gauss's law for magnetism, or magnetic fields, to tell us that there's no magnetic field component in the x direction either. Which means that the electric and magnetic fields, well, Gauss's law for electricity and for magnetism has now told us that in free space, the electric and magnetic fields are perpendicular to the direction that this wave that we're thinking about is traveling. Another way of saying that is this is going to be a transverse wave. Okay, so now let's think about applying Faraday's law to one of these sides. So Faraday's law then has to do with drawing a loop and the magnetic flux changing through that loop, producing an electric field. Okay, so let's just look at what the left side of Faraday's law is going to say here. And so we write out this path integral. And we already said that the x component of the electric field is 0. So this path integral along the top and the bottom are going to be 0. But we also have now the left and the right side. So the left side is going to look like that. The electric field multiplied by the path length. And then the right side, very similar, except for we're now at x plus delta x, still multiplied by the same path length, same length, left side and right side. So again, we're going to have this sort of issue where there's a sign difference between these two, right? Because we're imagining in this path integral, we have to just pick a direction for this path and follow it. And if the electric field is opposite that term is going to get a negative sign. So it looks like we're defining this loop as going counterclockwise. There's a little arrow at the top showing the loop going around this direction, which means that the electric field at x is counter to that direction. So this term is going to get a negative sign. So that's what the expanding out this integral looks like. And we can say a little bit more about what this term is going to be like. We use some of our good old calculus here. Tell us that the electric field at that plus delta x, if we let delta x go to 0, then that value is essentially, or approximately, the value at x plus the derivative of that thing multiplied by delta x. So it's like you're using the slope of ey and then multiplying by the amount it moves over to kind of get to that next point. So that's the derivative multiplied by delta x. Sorry, that x is a little bit not great. Also not great. So now if we replace this value in here, then these two terms are the same but opposite signs, so they're going to go away. So this whole path integral side ends up just looking like, looking right here. This derivative times delta x. Right? So that's like the left-hand side of Faraday's law. Well, what about the right-hand side? The right-hand side was this partial derivative of the magnetic flux, right? This changing magnetic field. And the magnetic flux is going to be it's actually this, I just write the one integral, but this integral is a surface integral. It's the integral over this whole face, right? So the amount of magnetic field lines that are going through this side 3. And then since we're imagining that delta x to go to 0, this side is very small and we can approximate the magnetic field on that whole face as just the magnetic field at the center of it. So this whole surface integral can just essentially be the average magnetic field multiplied by the area of that surface. Right, so that's, this whole brackets usually indicate to an average. And this is, I guess this is not the whole magnetic field. This is in the z direction, right? It's only the z direction of the magnetic field that's going through that face. Ooh. Need a finer marker. Like I said, we're letting delta x go to 0. So this sort of this average magnetic field we can approximate as that magnetic field at the center of that face, right? The middle of the face, or halfway between the sides. So this means our magnetic flux is looking like the magnetic field in the z direction at the center of the face multiplied by the area of that face. Yeah. So this was just doing a little bit more with the flux before putting it actually into the right side of Faraday's law. But now, put all the stuff that we have already into Faraday's law, right? Which should be minus the partial derivative with respect to time. Oh, I'm hesitating actually because I think I should have written A. We already used A for the face, for another face length, didn't we? For another area. Well, the side has an area of delta x times L. Right? That's just the area of that side. So this is delta x L. So I'm going to go ahead and replace that. And then if we put the left-hand side that we got, ended up with this, right? And now we have this delta x here and here. Get rid of that. Oh shoot, and I'm realizing we also should have had an L there too. Right? If I go back up, the left-hand side is this path length interval, so there should have been this L that was still tagged along. Here. So there was also actually an L there, which means those are also gone. And then finally, we want to use that information one more time, just that our delta x is going to 0, so this doesn't really matter, the fact that we had this magnetic field in the center. It's essentially now the magnetic field at X. Oh, and I didn't write it. It's also a function of t here. Never really been thinking about t that much, but it's there. And this one I also forgot. It's just the y component of the electric field. So all that got us to essentially the bottom left equation there. Right? That was from Faraday's law being applied to the side 3. If we were to have done this same process, the exact same process to say side 2, then we would have gotten this other relationship. And so these are relating essentially spatial derivatives of the electric field to temporal derivatives of the magnetic field. Or another way of saying that is that there's a spatially dependent electric field coming from this time-varying magnetic field. All right, just keep at it, keep going. So let's apply now the Ampere-Maxwell law to some of these spaces, and we're going to look at side 3 again. So what is our law looks like this. I'm just rewriting down. That. But we can be a little bit more explicit about what that flux looks like. It's actually this derivative, or sorry, this integral of the electric field over that surface. So this is technically a loop integral. This is a surface integral. Yeah, so I don't think, maybe I'm not going to go into the gory details of this one, but again, it's a very similar process as the last one we just did with Faraday's law, where you start to sort of think about the magnetic field components and the path lengths here, and then also the electric field and the surfaces. And after going through that gory process once again, which we can look at maybe in a class meeting if anybody wants to, but the result of it is that we get very similar relationships that we did for Faraday's law, or from Faraday's law. It's just now we actually have these spatial derivatives of the magnetic field related to temporal derivatives of the electric field. And again, another way of putting that is that there's these spatially dependent magnetic fields that are being sort of formed or created from time-varying electric fields. And the only thing extra in these ones is these permittivities. So the electric permittivity of free space, the magnetic permittivity of free space. Without dragging it on too much more, I ended up jamming a lot of stuff into one slide. So hopefully it still makes some sense. But we're just going to try to put all this stuff together. So from Faraday's law, we had that partial derivative of the electric field in the y direction, partial derivative with respect to x, related to the partial derivative with respect to time of the magnetic field in the z direction. So we're going to imagine taking a second spatial derivative of our result from Faraday's law, right? Just applying a second derivative to both sides of those equations. And then from our results from Ampere's law over here, we think of applying a temporal derivative or a time derivative to both sides of that. And right in the middle, now we see that we essentially almost have the same thing. We have the derivative with respect to time, derivative with respect to x of bz, right? And there's I don't know, I kind of went down a rabbit hole thinking about this, but the fact that you can actually exchange these partial derivatives turns out to be just fine in this case. And it has to do with something called Schwarz's equation, or Schwarz's theorem. I don't know, as the fact that both of their second derivatives are continuous means that you can just exchange these partial derivatives. So the middle two things are equal to each other, right? Which means the outer two things are equal to each other, which means that colored sort of equation on the left is true. Right? Second derivative with respect to space of the electric field in the y direction is related to this second derivative with respect to time of the electric field in the y direction. and it's equal, but there's that proportionality constant, epsilon naught mu naught. I don't know how many of you have done differential equations yet, but this is a standard one-dimensional wave equation, a differential equation. You have two time derivatives related proportional to two spatial derivatives. That's a wave. That's the differential equation that's telling you you're talking about a wave. So the general, or a general form of that is just use d as whatever general thing you're talking about. And it turns out that v squared in the general form, the thing that's squared and multiplied by the spatial derivative, or the secondary spatial derivative, that v squared, v is the velocity of that wave, it's the speed of that wave. So some other stuff that comes out of that, there's a solution to that 1D wave equation is just sine functions, cosine functions, right, things that do have this oscillatory nature. So we're just going to go ahead and pick the cosine function and say that its amplitude, we'll call its amplitude E0, just kind of labeling the amplitude of it as E0. And we could write it in terms of x and t, but also these other things come out of this differential equation. We get these other constants, k, which is known as the wave number, and omega. Omega is the angular frequency. And so given that that's the form of the electric field we get from that wave equation, you can use one of the other relationships we had for relating the electric field to the magnetic field from one of these relationships up here. We're not going to go through it. It involves integrating and differentiating, but you essentially get the same relationship back, or the same form of the equation back for the magnetic field in the z direction that's perpendicular to that electric field in the y direction, and we would get that. So applying Maxwell's equations to free space got us that there's this electric field and it's perpendicular to a magnetic field, and they're both sinusoidal, or they're both oscillatory. An interesting thing to point out is probably something that Maxwell had noticed while working through some of the, this kind of thing, the consequences of what he was proposing. And that is that from this, like I told you, in the wave equation, the thing that's multiplying the second spatial derivative is the square of the velocity of the wave. So if we look at what we ended up getting, well, we have epsilon naught mu naught, but it's actually multiplying the temporal derivative. So I'd have to divide to put it on the spatial side, the next side. What that means then is that 1 over that E naught mu naught is equal to the square of the speed of this wave. Or the speed is equal to the 1 over the square root of that. And these values, right, these values are just from, just associated with the electric field, the electric permittivity of free space, magnetic permittivity of free space. So these things were known at the time already, just because they knew a lot about electricity itself, about magnetism itself, and done a lot of work with experiments. So once Maxwell found out what the speed of this wave should be, plug all these values in. Oh, I'm going to run out of room again. This is the standard unit version of these things, SI units. 1 divided by square root of those two things multiplied. Well, you put all that in, guess what you get? 3 times 10 to the 8th meters per second. Bam, speed of light. So this was like a holy crap moment, probably, because, like I said, they didn't understand at the time that light, visible light, was actually an electromagnetic wave. But through Maxwell's work and the implications of Maxwell's equations, saying that electricity and magnetism produce waves, and these waves are what are traveling at the speed of light. So you gotta be like, oh my gosh, it's crazy. It's light. electromagnetic wave. And just one other thing to note too, also if you work through how you get from the electric field to the magnetic field, it turns out you find out in the process that the ratio of the electric and magnetic field is equal to, well, it's 1 over the square root of epsilon naught mu naught, which is c, we just call it c. That's the speed of light. Which also implies that the magnitude of the electric field is far larger than the magnitude of the magnetic field. 10 to the 8th times larger. Okay. So what the heck just happened? If you didn't quite follow all that, not surprising. It's tricky stuff and you don't really get it the first time around. But hopefully you will at some point. Or maybe you didn't get it. Very cool. Good for you. And I also had to do, I didn't work out everything in detail. Just jump over some things, a little bit of hand waving. But the result of that is that we sort of proved that in free space, the solution to Maxwell's equations are waves that look like this. They're sinusoidal waves where the electric field is perpendicular to the magnetic field. And the wave is traveling perpendicular to both of those things. Okay. It's a transverse wave. Transverse in 2 directions, actually. So this is a picture, but here's a little give. Right? So now if we imagine time actually marching on, then the wave advances, right? This is the wave moving, and we see, if you think about just kind of sitting at one point, like the very end of that wave that's shown here, you imagine sitting here and you had these detectors where you're able to sense the electric and magnetic fields, this is what would be happening, right? The electric field would be increasing and decreasing in one direction, say vertically, and the magnetic field would be increasing and decreasing in the other direction, say horizontally. And these things are happening in phase, right? As the electric field gets larger, the magnetic field gets larger, and then the electric field goes negative, gets larger, magnetic field negative, larger. Oh, just to note, unfortunately, this give is very nice. The colors are flipped from the picture before, so sorry for that. But I'm not going to make this again, so this is what you get. Let's just briefly think about maybe a more realistic production of these electromagnetic waves, and that would be something from an antenna. Right? An antenna, in this case, like this sort of dipole antenna. The basics of it are that it's just kind of this little piece of wire, and the charge in this wire is kind of going back and forth, so that one side is more positive, the other side is more negative, and then a moment later, one side is more negative, the other side is more positive, so the polarity of this thing just keeps flipping, flipping, flipping. The picture you end up getting is the same thing that I talked about a little while ago, where we just thought about this long wire carrying AC current, right? It generates a magnetic field that changes as the current is changing. So the blue arrow, or the blue dots and crosses, are showing that there's this magnetic field that at one point is wrapping in one direction around this antenna, and then from that changing magnetic field, we get this electric field looping through that changing magnetic field. That electric field is changing, so it produces another magnetic field perpendicular to it. And then, that's thinking almost of like one sort of instant, and then a moment later, the dipole has flipped over and it's becoming more negative or more positive on the bottom, say. So then the magnetic field from it is now flipped, and the electric field direction from that changing magnetic field is now flipped. Along the lines of this antenna, there's no current moving perpendicular to that line, so there's no magnetic field that's going to be created out here, so you don't get any electric fields created from that changing magnetic field that might have been there. So what you end up creating are these sort of like, I don't know what you want to call them, like weird ear-looking things that are created by this dipole antenna, and they just advance outwards over time. Right? They grow larger and larger, they start spreading out and advancing. So it can be rather complicated, very close to that antenna. Nicely enough, though, once you get a reasonable distance away from that antenna, say, 10 times the size of the antenna, once you get maybe about that far and even further and further and further, then, well, at any point along that wave front, it's essentially a flat wave now. It's sort of like the fact that we're on the Earth, but we're very, very far from the center of the Earth, so the surface just looks flat. It's a round surface, but it looks flat. Just because it's big and we are small.